Good day, gentle readers. Logos 2000, a study in 21st century foundations. Happy New Year. Today is January 1, 2025. And so at some point in time within the past 24 hours, it was 11:59:59.99999. The day before, and then at some point in time it became 2025. And so this is part of clock arithmetic, is usually called a modular. It's like the odometer reading of a car is that which proceeds in a pace in fractions around a wheel from 0 to 1 to 0 to 1 to 0 to 1. And so the clock arithmetic is a pretty cool, great thing, because it always just kind of increments in its increments compared to the field and the ratio, which is then kind of after we have an integer lattice, that the clock arithmetic increments itself in its modular increments in the clock arithmetic on the integer lattice. That then the integer lattice also makes for its fractions of the ratios of the rational, that after the mere increment and forward progression of time is that there's the whole idea of the division of time with regards to that the infinitely divisible and the infinitely divided, of course, are these most regular usual concepts all since antiquity, and all about the most usual kinds of things that go into that there are two rulialities, two regularities. The modular as built from either side that make it so that the idea of it as a concept has led to a certain particular idea of then what the numbers are to be continuous, that we have our standard linear curriculum for delta epsilon x after the laws of arithmetic and real numbers, and inequality for equality, because there's a total ordering of these numbers, as vis-a-vis then the ratios and the rational as that course being there to so follow, and for all what it makes for matters of convergence in the left-hand side and right-hand side respectively, compared to the clock arithmetic is different. It's according to a different way to look at continuity. So here that's the continuous domain of the line reals and the iota values are what makes clock arithmetic. And then the complete ordered field is what makes the arithmetic of the ratios and after the rational numbers. And then for the real numbers in this manner is the complete ordered field. That thusly we have at least these two models of continuous domains in mathematics. And Aristotle introduces both of these after Zeno's arguments, and then he picks one, and so most people read that as Aristotelian, but you can also say that Aristotle's continuum is the contiguous one, because that's the other one he introduces, whereas Eudoxus is, for whom it's given all this, the rational, after the Pythagorean, and for the real values and this kind of thing, because Cauchy, Dedekind, Weierstrass, Eudoxus is kind of the standard course. And then for Aristotle and Zeno, in a sense, otherwise there's the infinitesimals. That it involves that there's infinitesimals and infinities up front in the first kind of thing, instead of in the complete order of field, kind of the last thing, after the rationals, after the Pythagorean, after all that's put together. And as to why it's just kind of deferred until the very end, the entire problem of there being what is something that would otherwise be a contradiction that needs to be made this contradistinction, and then to be resolved in this manner so that thusly it's not an inconsistent theory overall. So here, by having continuity and infinity kind of up front and first in the theory and primary, central, fundamental, elementary, then thusly these kinds of issues are resolved. So one of the things about the clock rolling over is in distributed systems or programming, you might imagine you have like it's a fleet is what it's called, of nodes or units of computing. And so according to a directory structure or naming an information system, often called the naming and information system. For example, the domain name system, or as the way the internet has it so kind of arrived at, is that you have all these computers around the world, and they're each one in their own time zone. And so the world has its ephemeris, which is everything around it, and then it has a clock. The clock is basically just agreed that only two objects exactly together are synchronized at all, and everything else is just observing each other's clocks, and there's never really a particular instant that they're both the same. It's imprecise in that sense. So before getting into that, then the idea with the computers and timekeeping and journaling and auditing of events is according to their ordering in time, and this is one of the issues that arises, called the midnight problem. And that's when something is in a given range of time, then that's subdivided into its ranges of times by the rational. So the modular is what's arrived at. It's the modular and the modular and the modular again, which makes these even equipartitions of the time. Here is a continuous quantity and the prototype of this sort of continuous quantity. So if something arrives as related to day one and day two, if it arrives at midnight, then which one is it? And so the usual idea is that, because then all the data for that day is associated with a partition or a bucket of that day. And so according to the retention of data or retention in time, at some point in time, that day's bucket or its partition will be dropped and they'll just deleted. And so whether all the events that go with a particular group go in that bucket has that, to have all the related events go together for the group to be in the same bucket or partition is one of these things called the midnight problem. And it's really not so bad when you have it so that all the computers use a protocol to synchronize as often as possible to keep things according to the skew of the clock or the drift of the clock or the drift of the time according to space contraction affecting the Earth and affecting clocks. That thusly, according to this great timekeeping apparatus and the great synchronization of accords to a distributed protocol, the Network Time Protocol, or NTP, then there's a setup to be arranged that for the most part, at least computers usually agree on what time it is, only because they're so often coordinated this way, because otherwise the way it adds up to the usual idea of 86,400 seconds in a given day, of which there are 365.25 exactly in a given year, with regards to leap days and in leap years and the every 100 years and every 400 years the corrections for these things has that besides synchronization when everything is in the same time, then we have daylight savings time, which is a great thing because it's a requirement, or it's one of the great boons to have daylight to carry out anything that involves otherwise the expenditure of the lighting of things. And so the daylight savings time in its zones, according to the time zone database, for any given location, according to its authority and regulation, what is considered the time, has that when it rolls around the spring forward and fall back, the daylight savings time and standard time, then all of a sudden in two different time zones when they're comparing the thing, then the time of the event, then for one will be the day before and the other one will be the day after. And so then it gets into trying to, when making counts for these things and relating these things, that's called the midnight problem in this distributed computing, how to handle time zone changes with regards to the correlation of events. So that's just kind of a practical matter of trying to keep these things after it's kind of given that, well, all the computers all operate according to NTP, so that's the only way you can say they have the same time, because each clock count on each chip, according to its usually a crystal clock that given a particular regulated amount of energy at a particular regulated temperature, will have, according to the electrical properties of the piezoelectric of this, a quartz crystal, like a quartz clock, is considered very high precision, given the material properties, that'll arrive at the timekeeping apparatus is good. But then because they vary, even if just the least amount, no clocks have the same time. No two clocks have the same time, and it's just kind of because that's a matter of sampling, measurement, and observation. That by the time it arrives, some will have elapsed. So any kind of event in time is an extended body. Yet we want to think about these things in terms of being a distinct event and is happening a particular thing. It's kind of the definition of event. It's like it's a sample. That's what its definition is from probability theory and statistics. An event is a sample. Or sometimes it's considered multiple samples, or samples considered multiple events. But event and sample are usually synonymous, and the sample may arrive at multiple events, and an event can arrive at multiple samples. And then every sample of anything is according to time series data, because there's always implicitly associated with the event what time it is. And so that's what time it is according to the universal clock hypothesis. We have a clock arithmetic, and then the clock hypothesis is that there's one universe, and it has the time, the definite article. That then trying to figure out how to keep time series data as associated with these things is an effort in keeping synchronization up to date, as it were, and then as regards to retention and these kinds of things. So how this is also reflected in the mathematics of it and the physics of it is that in the physics of it, in science, there's what's called significant digits of time. And this goes for any sample. Any sample is qualitative and then quantitative. And the quantitative is what's the number, what's its measure. So you have sampling, observation, and measurement, or say sampling, measurement, and observation. Because to sample is to gather any sample at all. Measurement is to give it a value, and observation is that over time. So whether it's sampling, measurement, and observation, or sampling, observation, and measurement are two different things that have different reasons why they're in various orders. So the significant digits then arrives at that for any given measurement, there is what can be deemed as precision, how precise it is, and the imprecision, how not precise it is. So precision is the idea that within given tolerances, usually it's called, that you can say that something that's precise to a given tolerance will be no more than or less than the amount of the tolerance. And something that's imprecise has that all measurements, sampling, and observations are imprecise to at least some nominally non-zero degree. That otherwise they're pure numbers or perfect numbers, constants that are actually mathematical constants that have infinite precision, like pi or e or phi or 2 or any kind of number that's not said to be called a scientific number. And so the idea that then significant digits have is like so is that then following the operations of arithmetic, that what's the precision is just the number of digits then that are kept, and then it's like by an exponent or the order of magnitude. So you have the part that has the number of digits that are left, like 3.14, and then the magnitude is like 10 to the 1 power, or 10 to the 0 power equals 1. That according to all the negative and positive powers of usually 10, but it could be any given radix like 2 or pi or the constant of the natural logarithm. Usually it's considered in terms of powers and roots, so it's in logarithms, and it's with regards to the constant in the natural logarithm, or e. these orders of magnitude are considered to hold like so, and then the actual part of it for the scientific digits has that when you add two numbers and they have different magnitudes, then only the greater magnitude matters at all. The one with lesser magnitude, according to the tolerance of the greater magnitude, is basically zero. And then when you multiply two numbers, and what this gets involved is adding the powers of the exponents, and then multiplying the numbers, all that remains is the lesser of the significant digits. That according to the precision that carries in this, that is kept, that the imprecision grows in the treatment of arithmetical quantities according to their significant digits, and to remain at the minimum or the least of each of those as they're put together. So this is a great concept, and it gets into a lot of things that eventually then having something to like 3 or 4 digits of precision is considered pretty precise, because getting past that is up into thousands and 10,000s. And so for a given measurement, that's what our meter sticks and stopwatches have usually, as with regards to the idea that, human reflexes can operate in like 1/10 of a second. Or whereas though with regards to information processing capacity, that the brain's got millions of neurons and it operates as an analog computer, essentially an infinite speed though, then as with regards to what processing and the concurrence and the concordance of these things takes events. That human reflexes are to like the 1/10 of a second, and it was with training and with muscle memory, it can be less than that. And that consciously though it's not much more than that. And then similarly when looking at a meter stick, it's like you can only tell so far how it is to usually in powers of 2, like a half or a quarter, an eighth, a 16th, so 30 seconds. Usually we get down to 30 seconds, and that's being the limits. And then as with regards to 64ths, that's considered like either in music or in measurement, very, very much too precise. And in metric, of course, it's all powers of 10, and so then you just get into like as it's usually divided in terms of tenths, and that's just the way of things vis-a-vis powers of 2 for the imperial measurements and these kinds of things. So that just goes to help explain that then we have these things with regards to the representation of the numbers. And then for the arithmetic, there's that. And then for the, in computers, it's often called interval arithmetic. The idea is that you either have kind of a first-class type that, according to the arithmetic operations, treats it exactly as according to these rules for the significant digits of scientific numbers or numbers with precision and imprecision, and according to sampling, observation, and measurement, the precision and the tolerances. Or there's interval arithmetic. And then interval arithmetic is like, well, not only do we have it like that, but then the numbers we get out of this with the that actually live as floating point numbers, they have always a non-zero difference. So you can never really say that like 1 divided by 3 equals 1 divided by 3 in these floating point numbers, because one could be off at the very last 80th digit by a bit. And so instead you just say is 1 divided by 3 minus 1 divided by 3 less than epsilon. That epsilon is basically a number larger than this smallest possible imprecision in these floating point numbers, as with regards to why there's interval arithmetic vis-a-vis exact arithmetic. As with regards to the rational and the modular and the real and these kinds of things, why in computers there's no such thing as a real number's entire representation, including all of them. There is for all the rational numbers. It's called extended precision arithmetic. But then otherwise, then for something like a clock arithmetic between 0 and 1, it's just like as precise as it can be according to a uniform time base or the timekeeping norm. what establishes these units of what makes an integer, lattice, and increment, the modularity, and with regards to y, then when we're computing for real analytical quantities, it's all according to an analytical treatment. Then the computers and the arithmetical units don't have real numbers. All they have is finite numbers. And so then to do computer algebra with them, then we have what's called computer algebra systems. And so that just treats them as objects and has the expressions as regards to algebraic quantities, and then can reflect these things as with regards to them being pure quantities or constants of a given values. And then that eventually, when it's time to compute some numbers for them, that it's with a particular truncation of those, an approximation of those, is with regards to what's called numerical methods. So computers are not mathematically perfect, whereas time and a continuum mechanics is the idea. And there are theories where it's not. I mean, there are theories that everything is discrete and point light, but then instead, as mentioned here, we have continuity and infinity first. And in mathematics, it must be. And then in physics, it's also so. There's never been falsified time symmetry, and that furthermore, there are theories like the whole idea of the superstring theory is like closer to continuous, not continuous is the idea. So numerical methods are how to deal with values that are, according to measurement, sampling, and observations, that being events, have imprecision, how to add those up. And then also numerical methods are to say that when we have arrived at expressions that make for in the limit infinitary expressions that make approximations, that the imprecision in these concepts are as about the approximation itself, which is like it's some numbers that are close, like the rule of 72 or something like that. And then as with regards to the error term, which when left over is like there's always a nominally non-zero error term. And then in the cases where the infinitary expressions, that there's the deductive differences, deductively arrived at being not the result of the inductive inferences. It has that, that's when you say that the error term is non-negligible, that it can't be just discarded or put aside, because the whole idea of all this other stuff is like, well, whatever we can't say is precise does not exist. But then when those add up to make something that actually arrives at 0.001, eventually that will add up so that it's like, so what's negligible in a particular situation doesn't necessarily not what's said to dominate or to eventually make like a domino to topple over when it comes back into the equation in the system. So those are the terms from numerical methods about that an approximation is not exact, it is not a perfect number. Almost all sorts of computers work with that expectation of being in numerical methods, and it's close enough, and then tomorrow they just forget everything that happened the day before. So that's kind of how these things work. So that was what I wanted to talk about today, was the midnight problem and significant digits with regards to the precision of quantities or scientific numbers, scientific quantities, and then as with regards to things like interval arithmetic and machine arithmetic. And that after basically that there's the clock arithmetic, and there's the modular, and that clock arithmetic and rational arithmetic agree on the modular. They agree on the integer lattice, which is some basis of the vector space and of time or space. These what result then from those being ordinates, they're ordered, the coordinates. And as with regards to the origin, which is anyone's particular own center of the world, which is usually considered to be at infinity or at 0 or at 1, and where there's a metric and a time, the time. So let's see. What I found the other day was a book about numerical methods, and what it is, it's from Schaum's outlines. So these are study notes from a time when there was no internet, and so and books were dear, and so and copies copies were usually considered too expensive to do things. Like today's world where it's like, well, I'll just download the paper and read it on my PDF viewer. I mean, the old days that would involve like $5 at least worth of the copies, because copying a page basically has a cost of 5 cents. And so the idea that it was really readily available had that there was lots of ideas to make condensed versions, and that which kind of has the needful in one place. That Schaum's outlines were a great series, and so it's Schaum's SCHAUM, and Schaum's outlines has for a wide variety of things that. There used to be what was called Cliff's Notes for the literary and for many subjects. And so that would have basically summaries and synopses of things. And so these days that's what people are getting when they when they go to the search engine and just find some things. That's very common. And as after Wikipedia is kind of like a curated element of that. That's the dictionary, and the encyclopedia is that these days. And so then, but the Schaum's outlines were for matters of the technical, scientific, and engineering. And if there's one that I really particularly remember is that in like 1990 something, I really had a hard time finding anything to explain tensor calculus and definitions of tensors at all, which here considers as quantities that end up preserving what are the vectorial was with regards to the coordinate and coordinate free here. So with regards to covariant, contravariant, and conventions, and what that means with regards to the tensorial products as with regards to the vector products. And that being is with regard kind of like to the real analytic and the complex analytic. So what I found at some point in time was Schaum's on tensor calculus, and that was one of the best. That's where I learned about contravariant and covariant and a bunch of these things, because it was hard to find that in the books because it was always just kind of given as a given. And then later when I encountered it in like university courses or something like that, then it was a lot easier because sometimes the instruction wouldn't really give too much detail about them except to just give the accounts of how to operate on them, or as usually by then it was kind of in this linear analysis, linear algebra setting, and it kind of had that there's a lot that goes into the reasoning why these things are mathematical, and so it was a great thing. So what I found here was this Schaum's on numerical methods. So I thought I'd take a look at that today and see kind of what coverage it gives to things. Because in numerical methods, what we learned about things like Newton's method, and Newton's method is named for Newton, and it's a means to use some numerical substitutions to arrive at shorter forms and approximations. So when you can find closed forms, then those are finite, and so you can say they're kind of perfect when they're closed forms. What it does is it arrives at approximations, and so you can say that it ends up being close. And so Newton's method is usually considered with regards to binary search, and then there's another one he has is with regards to the whole Pascal's triangle bit, and then flipping and rotating that Pascal's triangle to arrive at then in one that has like the infinite case for the Pascal's triangle, and then you use that, and then another kind of corner case of it to make for more readily computing pi. And so he's able to arrive at more digits of pi by his numerical method. Numerical methods, when they're deemed to give the value of a constant, and something like the first so many digits of e or pi or phi, these transcendental not ratios, constants, not ratios and not algebraic, being the solution to a polynomial equation with integer coefficients, the real ones being rational or algebraic. These constants are transcendental, so their digits in their pure constant are infinitely many, and they never repeat. And so finding an algorithm to find them is kind of a thing. And in this case, it was possible to arrive at many more of those than had been arrived at via the ancient method of dividing the circle up and then just boxing out more and more computations. That is to say, these numerical methods often start running to page after page after page of computations, because at each step of the iteration, you start with like the first term, and then the second term, and then the third term. At each step of these terms, it gets more and more computation to arrive at the next value, and then you just kind of sum those up is usually the idea, or they make a sequence or a series, these terms. So Newton had some good numerical methods, and they probably were arrived at in part by him, but definitely with the influences and assistance of the other people, the entire enterprise that was kind of so arrived at, or from Cambridge and Oxford in those times. And there were many resources that were classical resources, and as of the earlier Enlightenment, or as after the medieval times, and after the times, that many of these things are rediscovered again or recycled, old wrapped as new. But that's not really to cast any more shade on Newton. Yet the idea is that he also came up with some great things. And then it as well helps to see kind of where he arrived at. The other day that I saw something that helped explain that out of Pascal's triangle was just kind of made this idea of the case for the infinite and then the oscillating in the infinite ones, and then the plus minus one oscillating, to arrive at how Newton made his formula that's an approximation. It's a numerical method to arrive at an approximation for pi. And so that was pretty good. So Newton's method is usually introduced in the classes for numerical methods as like how to find roots, and then later it's also used for calculus and these kinds of things. And then the Taylor series is another one. It has the way the form is that given the derivatives and to compute off the factorial, that it starts giving terms that are close. And as with regards to all these kinds of things, and then as with regards to the means of numerical methods, and then the methods according to the ordering of the numbers, the inequalities, to arrive at finding the bounds of these error terms, so that you can say an approximation is good up to a given order or degree. These are part and parcel of numerical methods, is what it's called. Making approximations that are good. And being able to prove that by establishing the bounds on the error term. So it's. So this outline is by a mathematics professor out of Boston or so, Francis Scheid, Scheid, including 775 solved problems, completely solved in detail, from McGraw-Hill. So this is from about 1965 or 1968. And here, before, there has been looked at some books in numerical methods. Like there was that one about approximation algorithms for polynomial and non-polynomial problems. And otherwise, I have some texts in numerical methods. Usually, a good college textbook in numerical methods would be something to get into. Um, but it's used in so many things to make it possible for computers to come up with numbers. That it's quite a wide and diverse field. And then sometimes you'll find that some methods are just kind of, once they're found to apply, then they're used like implicitly in the arithmetic and the algebra everywhere. And then it needs to kind of be taken into account why that is so. And then when it's made so that the reason why that those are used for everything, even when there are different ones with better bounds, is because it's kind of just considered as a library routine and de facto or implicit, and most people don't even know, or it's just not as arrived at. Yet it's definitely critical to any kind of design of experiment or for engineering's sake that it's formal, that numerical methods always have a nominally non-zero error term. They're not perfect. Computers are not perfect, the computators we have. Mathematics is perfect, and you can program a computer to do symbolic algebra as perfect as a mathematician. How that's arrived at then is with regards to then, otherwise their numerical methods that can solve pretty much any kind of formula that otherwise would require a symbolic treatment, and having to do the derivations is considered doing mathematics, and programming that is its own kind of thing. Computer algebra systems like Maple or Maxima or Mathematica involve these on the computer algebra side. Then also they just have solvers which use numerical methods all the time. So I thought I'd just kind of leaf through the table of contents of this and take a look at and see, get a kind of a survey of this. 1968. The popularity and explosive growth of numerical analysis today are further evidence that applications are still the leading source of inspiration for mathematical creativity. And so this is, I thought this quote was pretty good, because it helps to express that this is the applied. This is applied pretty directly, and it's really apropos in the engineering sense, because you got to get numbers somehow. And so the idea then that this matching of the physical models and the mathematical models and the numerical models and the computational models, these being four different things, as if that's applied to put them all together, still we can have a theory where that's all one theory, that the pure and the applied have it so that that mathematics is geometry, or foundations is pure mathematics. Have it as well, it's also applied. And so whether creativity comes from this or that, is some people have that it's just the numbers themselves and the objects of the theory of mathematics, the universe of the objects of mathematics. And the other one is that it's like everything else that it's about. And so that's still this. It does go to show that this author is enthusiastic about numerical methods and about the applications so preferred and the many of them. Whenever new mathematical ideas are developed, it's usually new applications which have pointed the way. And so this gets into that. Well, yeah, a lot of times it's like to come up with something. It's like mathematics does not explain it, so add a factor and then figure out where it fits until it does fit. And then we have to figure out how that is arrived at. It's kind of reverse engineering in a sense. And here he gets into computers. The electronic computing machine is itself an illustration of this, a response to an overwhelming need for faster computation. And the appearance of such machines has made it possible to meet the demands of today's applications, in many cases by developing more sophisticated numerical methods. So there's this guy named Leontief, and he took like 85 variables of the entire economy, and then started crunching numbers with some linear analysis techniques he had developed, and making heavy use of numerical methods. And so Leontief is given as one of the great examples of the applied and in the computing resources of the time that was just kind of considered as like, well, that's why computers are good, because it came up with all this numbers each day with regards to the values, the samples that arrived in the same kind of time. And so it became actionable intelligence, say. And while that is so, these are subject to the limits, and we have our the necessary careful design of statistical experiment and hypothesis, vis-a-vis the empirical, which is like, it looks good, it seems close, and these kinds of things, which is not formally guaranteed, and it can't be blamed when it's wrong, is that kind of thing. And it is nominally non-zero, the chance that it's wrong, when it's that way. And the appearance of machines. Modern numerical analysis. It is the numerical aspect of the broad field of applied analysis. Oh, and then the author goes on, he says, it would be a mistake, however, to draw too fine a boundary between our subject and what is called pure or abstract analysis. The borderline is a fuzzy one, as borderlines usually are, and materials from both sides frequently infiltrate the other. In earlier days, it was commonplace for mathematicians to be expert at both the pure and the applied. Both have long since developed to a size which makes full acquaintance with even one impossible, and reasonable competence at both an arduous objective. For example, I'm not the world's greatest analyst by any means. I prefer to have all the concepts available so that no matter what it is, it's mathematics, say. In spite of this, the applied mathematician, including the numerical analyst, must try to keep aware of what is happening across the border. To this end, it has been one of my objectives to provide occasional evidence of infiltration, at least in elementary ways. So he's helping to show when, for example, two different numerical methods collide, or their error modes of them. The treatment of Taylor series is one such example. The importance of these series in pure analysis is classical, but they are also valuable for computing functions, estimating error, and so on. This is like with the infinitary and the limits that are arrived at, and like the Fourier, after the Fourier style analysis, the infinitary and the limits, and that's in after the Newtonian and after the Eulerian and these kinds of things. After algebra and analysis and the Muslim Enlightenment of Al-Khwarizmi and Al-Jabbar for algorithms and algebra, Fourier series, orthogonal polynomials, and perturbation series, just to mention a few, are other topics which are valuable on both sides of the borderline. So it's kind of like transforms with regards to like the Fourier transform or the Laplace transform. It's like, well, if you can find any pair of orthogonal functions, you can make a transform, and then it makes all this stuff in the functional analysis, and it makes a setting for the treatment of these as regards to the equations defining each other, all these kinds of things about it. And so it's similarly so with these building blocks, which make for the numerical methods. The proof of the classical existence theorem of differential equations by applied methods is a beautiful illustration of how applications lead eventually to abstract theory. Now, here there's also the resonance theory, and the differ integro and integro differ again. So some of these things are considered just part of like, well, eventually that just kind of sits only in differential geometry there, and we have bigger functions in that. But it does make a good point as with regards to that these are the way that these things are arrived at. So, although our principal interest here is numerical mathematics, a number of topics usually relegated to other places will be presented briefly, because they are themselves useful in computation, and even more important, because they are a reminder of the fuzzy borderline and the value of infiltration in both directions. The numerical analyst is, after all, an analyst. And then how this is set up is he's got... he'll introduce some terms, and then he'll set up some problems in it, and then show how they're solved. And the contents has here, let's see what he says. What is numerical analysis? The collocation polynomial. So that gets in the whole collocation bit, as with regards to the ideas of what's going on with the hypercube distance and the Zeno's swath, and this kind of thing, and the swath integral, and the hypercube. Finite differences, factorial polynomials. So finite differences are like, with regard, before the differential, there's finite differences, and that's the kind of the land of concrete mathematics a lot of the times. Factorial polynomials, and this is with regards to that the polynomial grows at a certain particular rate, and then as with regards to that and the Taylor series and all this kind of stuff that gets involved. Summation. So these are terms, and then when the sums arrive at things, again, this is kind of concrete mathematics is where a lot of the stuff kind of grows from. The Newton formula, operators and collocation polynomials, unequally spaced arguments. And this is for when you kind of have like bounding boxes, and then they can be figured to be of a size. And so it's kind of like, instead of having like Riemann sums or Lebesgue sums, which are like they're a given particular width that is constant and equipartition and goes to zero, these are when they're kind of unequal to add up. Divided differences. Think about when you have the different operations of arithmetic and where they meet, like 2 + 2 = 4, but 2 × 2 = 4, and 2 squared = 4. Is with regards to then like phi is equal to 1, phi minus 1, or is equal to, or phi minus 1 is equal to 1 over phi. That's like AXB is equal to AYB. Or otherwise, just this idea of divided differences, I think, might be related to that. Osculating polynomials. Now, it's important to distinguish the two words. Osculating, like that's something that is periodic and goes back and forth, oscillates, with osculating, which means it's like after kissing that they touch. Like two circles is where they arrive at the same point at intersection or a tangent together, that they're coincident. That's the osculating, not the oscillating. Osculating polynomials. The Taylor polynomial, associated with differentials in the factorial. Interpolation and prediction. So interpolation is a great idea. And interpolation and extrapolation are very closely related. And what they mean is, given a particular number of points, how they point at the next point. A line through them points at the next point. So interpolation and extrapolation are a lot the same. And so interpolation is kind of like the prior, and extrapolation is kind of like the posterior. And so a lot of these numerical methods arrive first from graphical methods. It's like, well, you draw the events on a chart, and then you see if it looks like a line through them, and draw the line through them, and say that looks like the function for this formula for these dots that makes it so that the sum of squared differences is least, for something like that. One of these methods eventually is called least squares, and least squares for linear finding a line, or finding a function that expresses the value of these things, gets into all the statistics and the sum of squares of differences or the least squares, as it's called. The least squares is one of the first introduced methods of helping to find a relation among events. And so statistical analysis is often about trying to find a relation among events, because the whole idea is to figure out, it's like, here's data, what's its distribution? And then once it's figured out kind of what's its distribution, is like, does that represent a formulaic relation that is possible to assign to particular elementary functions? And then can it be possible to make predictions, or to then also to validate the theories, because the mathematical theories only have these mathematical relations to either falsify or not falsify, that the statistical hypothesis is invalidated or not invalidated, these kinds of things, that there's no validated, there's just not invalidated, there's no verified, they're just not falsified, because that the error terms are nominally non-zero. And then a good theory is like, subject to many trials, never falsified. That's the idea, that over time, that's all in time series data again, and these kinds of things. So yeah, with regards to interpolation and extrapolation, those are closely related terms. And so interpolation is generally the idea, and then extrapolation is kind of the space inversion other side of that. Numerical differentiation. So this is to arrive at, given a formula, how to, well, you can just plug in numbers to get the value, but then given you take the derivative of it and say, well, what is now the derivative of this? Is this numerical differentiation? Often after Newton, then we have like Runge-Kutta and various means of numerical differentiation. Numerical integration, Gaussian integration, singular integrals. Now, if you recall from our discussion with Neri and stuff like that, it's like, how do we even solve that with analysis to come up with the pure numbers, the pure forms and that? Then here it's like, as with regards to it here in numerical methods, sums and series, difference equations and differential equations. So these go into figuring the parts as then like the sum of partials, all the stuff about the Laplacian, like the new idée fixe here about the Duhamel principle, and that being an infinitesimal bit of the generation resulting being the same as that being the Lorentzian after the Laplacian, that these are just these things put together, and then it's like, well, it's always fallen apart to arrive at that in the analysis, that these are the kinds of things. Differential problems of higher order, least squares polynomial approximation, min-max polynomial approximation, approximation by rational functions, trigonometric approximation. This would be usually the small angle approximation, because as sine x and x go to 0, then it's like they equal the same. Or as x goes to 0, the x and sine x are the same, is like in the infinite limit, is used in a ton of different places, because then you can take something that's a trigonometric function and replace it by a linear function. And so again, nominally non-zero error term, and it is an approximation, and so its presence in algebraic derivations in physics is always in a sense broken. It just to make it so that, because all the numbers that go into that are scientific or the quantities are like so, that because it is in any way at all a numerical method, it's formally having a corner edge case there. Trigonometric approximation, nonlinear algebra. So I'll be interested to see what would be described there, because that's usually, it's either it's like, well, it's circular somehow, and there's a way to solve it, or it's like it's not linear and there's not a way to solve it. But there's like simulated annealing and this kind of thing. This is where the idea is like, if we could perfectly anneal, to weld together, to anneal like two surfaces, is to like weld them together. And this, so the simulated part of that is like, can we approach that in the limit as a finite element analysis? It's one of these kinds of things. Linear systems, linear programming. So linear programming is usually kind of finding like convex hull, or it's finding for integer programming and linear programming how to find minima and maxima. Overdetermined systems, boundary value problems, and Monte Carlo methods. Monte Carlo methods is like, we'll throw darts at the dartboard and see what the shape of the donkey looks like. So that's just kind of a survey of this very, very cursorily. What is numerical analysis? The algorithm. So he's got a diagram that says input information, the algorithm, output information. And then the second key item is the presence of error. And he says, and he's got another diagram. In the first box is input errors. The middle box is algorithm errors. This is the error term, as we mentioned. And the last box is output errors. So his third section here is supporting theory. Though our view of numerical analysis will be applications oriented, we will naturally be concerned with supporting theory. Often the theory to which we are led has intrinsic interest. It is attractive mathematics. Primarily, however, the theory is important to us because it contributes to the search for better algorithms. Solve problems. And so then it gets into things like multiplication as an algorithm. And then it describes a multiplication by the usual algorithm with carrying ones and then doing it modularly and then doing that for the next place and then adding up those terms. And then he has this one called the Russian peasant algorithm. This method involves continually doubling one factor while halving the other, noting where the halving leaves a remainder. So it's using carry. That the part of the algorithm is carry is like what connects these things together. That the carry bit or the carry for the sign, but the carry though is used in all these different kinds of algorithms. So why aren't people taught this other kind of algorithm for multiplication at the same time they're taught regular multiplication? Well, first everybody's got to know at least one. That's a linear curriculum. And so that everybody can come along later, way later in the curriculum and be shown and demonstrated from beginning to end how something can work. But this other way works just as well. It just kind of uses paper in a different way. And that gets into like some things can be linear and then just grow, whereas other things are like diagrammatic, as with like we'll carry it out this side and then carry it around and carry it down in this way and this way. Then he talks about measuring two lengths approximately, 3.32 and 5.39. The symbol tilde representing approximate equality. So tilde is used to indicate relates. Sometimes it means not, but usually it means relates and approximate. And so when you see it over an equal sign, it means approximately equal. Compute approximations to ... by three-digit addition. And so three-digit addition basically just says that all that he's keeping is a uniform length of 3 digits by rounding off whenever necessary. So this helps introduce, after carry, there's rounding. And so rounding in the significant digits is key because it's like, well, we have to throw away the last digit, but those would add up. And so it's like, well, if what you have left is above 0.5, keep it. If it's not, then discard it. So a keep or toss is the idea. So yeah, rounding, and as regards to the ideas of there's the ceiling is the next higher value, any greater than according to the last digit. And the floor is the lower one of that. So like the ceiling of 1.5 is 2 and the floor of 1.5 is 1. And then the rounding has that 1.5 would round to 2 because you always round up. But when you think about something like negative 1.5, you might round either away from 0 or towards 0. So rounding up is usually called rounding away from 0. And so negative 1.5 would round to negative 2. But sometimes you have, because when you're just considering negative numbers, meaning just like backwards from this one kind of thing, whether you round up or down, whether you round up all the way along the line or whether it's rounding towards 0 or away from 0, are these various kinds of ideas that get into why they're rounding in all the algorithm of why things are so. And then he has some more exercises with more digits. Find the smaller root of the quadratic equation, x squared minus 20x plus 1 equals 0. So in the quadratic equation, there's this wonderful thing called b squared minus 4ac over 2a. Square root of b squared minus 4ac over 2a. So the coefficients of a quadratic equation are ax squared plus bx plus c equals 0. And so the coefficients a, b, and c then have that's the quadratic formula. And so it gives, it's a closed form for what those are. And I really, at this point in time, because the quadratic and the parabolic are so everywhere in all of physics, then I'm going to be studying the quadratic formula some more. But that's about where we'll close today, because we've come up across the hour pretty well. We're talking about rounding and carry and algorithms of arithmetic, and then what happens when there are only finite resources of those. The computer only has finite resources, but it can be programmed to do algebra and arithmetic and analysis just like a human being can. It's called symbolic. And so then as with regards to the numbers and measurements you make, they are only as precise as they can be, and with regards to sampling, measurement, and observation. So then as with regards to that for numerical methods today, in Logos 2000 today, what's been kind of addressed is the applied mathematics. And why in our theory, for the foundations, it's a pure mathematics. But then as well, with regards to the science of it, that for physics and statistics, it has to have, for science, that science and statistics have this is like so. And that our mathematics and logic and even our physics is not necessarily a science. It's theoretical, these objects. And so then as with regards to that, then that's a brief introduction to then knowing what you can make of things, and measure twice, cut once is usual idea. Because measurement can be free, whereas as cutting is a permanent kind of a thing, is about the most usual thing to say about that. And then with round and carry, that you learn in arithmetic to carry when you're doing all the algorithm of the perfect numbers put together. Like integers, it's like to every penny, the least amount. The operations of arithmetic and integer arithmetic for the integer lattice. Then for the clock arithmetic and these other continuous domains, that's a part and parcel of why. And then our finite world, there are all these kinds of numerical methods. For dynamical modeling, which is all the continuous stuff, and then numerical methods, all the finite stuff. Have a great day. Have a great year.